right? So we classify semiconductors into two. Number one, intrinsic semiconductor. I'll put simply SC, means intrinsic semiconductor. And second one, extrinsic semiconductor. We have two types. We classify semiconductors into two, intrinsic and extrinsic. Remember, intrinsic semiconductor means pure semiconductors, pure. Okay, if you take pure silicon, pure germanium, that means you should not add any impurity, that's all, right? Pure silicon, pure germanium, pure gallium arsenide, okay, pure silicon, pure germanium, pure gallium arsenide. These are all few examples for intrinsic semiconductors. Intrinsic means you should take pure semiconductors without adding any impurity. Okay, it's called intrinsic semiconductor, right? What is extrinsic semiconductor? In extrinsic semiconductor, okay, we add some impurity to the host crystal. Okay, the host crystals are these, right? Suppose you take silicon or germanium or gallium arsenide. Many examples are there, etc., etc. We call these as host crystals. Host crystal. To this, we should add some impurity. We should add some small amount of impurity so that you will get what is called extrinsic semiconductor. Okay, so if you take only this material, it is called intrinsic. But to this material, if you add any impurity, you will get what is called extrinsic semiconductor. Okay, so you will get extrinsic semiconductor. Addition of impurity to a pure elements or pure compounds like this is what we call, this process is called doping. Addition of impurity to pure elements so that if you create extrinsic semiconductor, this process is what we call as doping, right? So extrinsic semiconductors are also called as doped semiconductors. Okay, extrinsic or doped, because we have doped with some impurity. So this is the basic difference between intrinsic and extrinsic semiconductor. Intrinsic means pure material. Extrinsic means to the pure material we add some impurity. Okay, yeah. First, let us start with the intrinsic semiconductor. We will discuss about intrinsic. Okay, we'll get some idea about that. Then we'll discuss what is called extrinsic semiconductor. Right? Okay. Now, so what is intrinsic semiconductor? Intrinsic semiconductor. Okay. I have told you intrinsic means pure. So in periodic table, group 14 elements, not all elements, in group 14, the elements like silicon, germanium, right, they show, they behave like intrinsic semiconductors. Similarly, this is elemental, right, in group 14, this is elemental semiconductor. For elemental semiconductor, we have chosen group 14 elements, silicon and germanium. They show, they behave like semiconductors. These semiconductors are examples for elemental intrinsic semiconductor. We also have compound intrinsic semiconductor. Compound semiconductor. Last class I gave all these things. Okay, anyway, no problem. Gallium arsenide, indium phosphide. Okay, plenty of examples are there. Aluminium, gallium arsenide. Okay, compounds also can act as intrinsic. This is also pure. Don't think that gallium arsenide means it is a mixture. No. Gallium and arsenic form compounds. Okay, these compounds, right, are pure. These are all pure materials. So pure gallium arsenide, pure indium phosphide, pure aluminum gallium arsenide. Okay, so these materials can also act as intrinsic semiconductors. Okay, so remember, in intrinsic you can choose elemental semiconductor as intrinsic. You can also choose compound semiconductor as intrinsic semiconductor. Okay, now I'll give how intrinsic semiconductor conducts current. Okay, I'll take silicon as example and I'll explain how this happens. Okay, now listen. I have told you whether it is intrinsic or extrinsic. For semiconductor, this is the main thing you should keep in mind. Band gap should be less than 3 electron volt. This is very important. Okay, whatever may be the semiconductor, for any semiconductor, band gap should be less than 3 electron volt. Okay, yeah. Now, so in intrinsic semiconductor we have examples with the elemental and we have examples with the compounds. Good. Now I will give explanation how intrinsic semiconductor conducts current. Okay, using silicon as example. Students, if you take pure silicon crystal, in pure silicon crystal, adjacent silicon atoms. So this is one silicon, this is another silicon, right? In the crystal, we have plenty of silicon atoms. Okay, this continues three-dimensionally in all directions. Okay, and between one silicon and the adjacent silicon there is a covalent bond. Okay, there is a covalent bond. Let me show the covalent bond like this. Okay, this is a covalent bond. In this covalent bond, each silicon atom shares one electron. This silicon atom share one electron, that silicon atom share one electron. So both the silicon atom shares the 2 electrons. Okay, similarly between these two silicon we have a covalent bond. Between these two silicon we have covalent bond, like that. Okay, so in the entire crystal of silicon, the adjacent silicon atoms are connected by covalent bonds. It goes like this. Okay, this is pure silicon. Students, remember, this is very important. For silicon atom, silicon atomic number 14, silicon has only 4 valence electrons. Silicon has 4 valence electrons. Each silicon atom has 4 valence electron. So listen, suppose if you take this silicon, see this silicon contribute the 4 electrons in the formation of covalent bonds. Therefore, all the 4 electrons of silicon, okay, are involved in the covalent bond formation. Students, listen carefully. Covalent bonds are strong bonds, somewhat strong. Therefore, these electrons are localized electrons. The electrons in the bond, students, the electrons in the bonds are localized. Right here, electrons in the bonds. Okay, they are all localized electron. They cannot move. So these electrons do not conduct current because they are localized. They are tightly bound in the covalent bond. They cannot move. They are called localized electrons. Okay, therefore, pure silicon at 0 Kelvin, I'll take at 0 Kelvin. At 0 Kelvin, it does not conduct current. 0 K. Okay, it's not okay, it's 0 Kelvin. At 0 Kelvin, it does not conduct current. Why? Because all the electrons are localized. Okay, so there is no free electrons to move, or there is no electrons to move. Therefore, conductivity is 0 actually. Conductivity is 0 at 0 Kelvin. But what happens at room temperature? we are using silicon materials in room temperature. Okay, if you come to room temperature, what will happen? Some of these bonds starts to break. Okay, breaking of covalent bond takes place. Therefore, the localized electrons, okay, now starts to move. So let me just show you in the next page. Using band, I'll show you. Yeah, I have told you in the last class that in the case of silicon, you'll be having what is called valence band. Let me draw like this, and we will be having conduction band. Okay, this is valence band and this is conduction band. This is energy axis. Energy increases in this way. Students, remember last class? Okay, I discussed all these things. When many silicon atom combine, bonding molecular orbitals form valence band and anti-bonding molecular orbitals form conduction band. I have told you. And between valence band and then conduction band, there is a gap. This gap is what we call as band gap. Suppose if you take silicon, this band gap is 1.1 electron volt. Each and every material, okay, has a specific value of band gap. Okay, for silicon the value is 1.1 electron volt. Students, listen carefully. At 0 Kelvin, and I also told you the valence band is fully filled. I have told you. I'll use pencil. This valence band is fully filled in the case of silicon, and conduction band is fully empty. Okay, this is fully filled and this is fully empty. Okay, so here I have lot of electrons. Valence band has lot of electrons, but the problem is at 0 Kelvin, the electrons in the valence band, they do not have sufficient energy to jump to conduction band. At 0 Kelvin, right, electrons, right, in valence band cannot undergo transition, from valence band to conduction band. They cannot undergo transition. Why? Because at 0 Kelvin there is no thermal energy. Students, listen carefully. 0 Kelvin means no thermal energy. When there is no thermal energy, the electrons present in the valence band, though we have lot of electrons here, they are all localized electrons. They are all localized. So they cannot jump out. Therefore, the material do not conduct current now. But if you go to high temperature, okay, at temperature, if temperature is not 0 Kelvin, if it is above 0 Kelvin, say for example room temperature. At room temperature, what will happen? Listen, the electrons present in valence band, they get sufficient thermal energy. The electrons present in valence band, they get sufficient thermal energy and jump to conduction band. So when they jump to conduction band, what will happen? The place where the electron present become positive, and now the electron enters here. That electron carry negative charge. So this is positive, this is negative. We represent positive charge with a circle. We call this as hole. Student, this is called hole, and this is the electron. Okay, or conduction electron, also called delocalized electron. Okay, I'll call this as conduction electron. Okay, so listen carefully, students. At 0 Kelvin, electrons do not have energy to jump, but at temperature above 0 Kelvin, say for example at room temperature, okay, electrons undergo transition undergo transition from valence band to conduction band. What happens? Because of this, a hole is created in the valence band. You'll get a hole. You'll get a hole in valence band, or holes. I'll put holes in valence band, and electrons in conduction band, okay, are created. I have shown only one transition. Like this, many electron undergo transition. So you'll get many holes here. You'll get many holes here. Many holes are created in valence band, and many electrons starts to appear in conduction band. Students, any doubt up to this?
No, sir.
Hello, students. If you have any doubt, you can ask me.
No, sir.
So listen. This is pure silicon. I didn't add any impurity. In pure silicon, band gap is 1.1 electron volt. So at 0 Kelvin, the electrons, they do not have sufficient energy, so they cannot jump to the conduction band. Therefore, at 0 Kelvin, okay, silicon is not a conductor. It's not a semiconductor. It will act as an insulator actually. It will act as an insulator. At 0 Kelvin, right, silicon acts as an insulator. But if you go above 0 Kelvin, if the temperature is high, say for example room temperature, then electrons undergo transition from valence band to conduction band. So electron move from valence band to conduction band because these electrons now gains energy, thermal energy, and therefore jumps here. So this transition is what is due to thermal energy. Okay, so this is called thermal excitation. We call this process as thermal excitation. Okay, so in intrinsic semiconductor, electrons and holes are created. Electrons appear in conduction band, holes appear in valence band. Okay, the electrons in conduction band, they are not localized electrons. They are actually delocalized or free. Okay, so these electrons, right, they conduct current. Listen, students, this is very important. For each transition, I'll get a hole in valence band, I'll get an electron in conduction band. For each transition, we'll get a hole in valence band, and an electron is created at the conduction band. So now, listen, in intrinsic semiconductor, this is a very important point you should keep in mind. In intrinsic semiconductor, number of electrons in conduction band should be exactly equal to number of holes in valence band. Students, remember, holes means positive charge. Okay, because when electron goes there, it leaves a positive charge here, because previously because of the electron, okay, the material is neutral. Now electron is jumped from valence band to conduction band. Therefore it will create a positive charge in valence band. These positive charges are represented as circles, also called holes. Okay, so you'll get holes in the valence band, and you'll get electrons in the conduction band. And the point that is very important here is, okay, in the case of intrinsic semiconductor, number of electrons in the conduction band and number of holes in the valence band are equal, exactly equal. And electrons and holes are generated due to thermal excitation. Only because of thermal excitation, the electrons and holes are created. Okay, what happens if you increase temperature further, students? If you increase temperature further, what will happen? As temperature increases, you will get more electrons and more holes. Okay, see, as temperature increases, okay, more electrons okay, in conduction band and more holes in valence band are created or generated. Okay, as temperature increases, you'll get more electrons in conduction band, more holes in valence band. Okay, and remember, students, any doubt up to this? If you find any difficulty, you please tell me, I will help you. See, the basic idea is this. In semiconductor, you will be having valence band and conduction band. Between them, there is a gap. That gap is called band gap. Okay. Valence bands are fully filled. Conduction bands are empty. Remember, the electrons in the valence band are localized. They cannot move. So at 0 Kelvin, there is no thermal energy available. Therefore, these electrons cannot jump to conduction band. But if you go temperature above 0 Kelvin, okay, or at room temperature, for example, what will happen? The bonds, the covalent bonds, okay, the previous page I have shown you these covalent bonds. These bonds starts to break. Okay, when they starts to break, what will happen? The electrons gain thermal energy, right? Therefore, the electrons from valence band undergo transition and enters into conduction band. This is called transition. Okay, this arrow mark indicate transition. So electrons undergo transition from valence band to conduction band due to thermal energy. That is why this process is called thermal excitation. Right? When one transition occurs, I will get one hole in the valence band, one electron in conduction band. Since in intrinsic semiconductor, this transition occurs only because of thermal excitation, number of holes in the valence band and number of electrons in the conduction bands must be equal. Okay, and if you increase the temperature further and further and further, you will get more electrons in the conduction band, more holes are created in the valence band. Okay, students, this is another important point. Keep this in mind. Electrons in conduction band and holes in valence band. Okay, if electron present in conduction band, right, they conduct current. Similarly, if holes present in valence band, then also they conduct current. So remember this, very important. Electrons, if electrons produced in conduction band, yes, material conduct current. Similarly, if holes generated in valence band, then also the material conduct current. So here conductivity, electrical conductivity is not only due to electron. Electrical conductivity is due to electron as well as holes. Okay, so the material conduct current, electrical conductivity of the material, electrical conductivity of semiconductors, right, are due to, right, electrical conductivity of semiconductor is due to the mobility. Mobility means just understand like this, it is a movement, right? Movement is due to the mobility of electrons in conduction band and mobility of holes in valence band. Note down, this is very important. Electrical conductivity of semiconductor is due to the mobility of electrons in conduction band and the mobility of holes in valence band. Very, very important, students, keep this in mind. Very, very important. So whenever holes are generated in valence band, yes, the material conduct current. Similarly, whenever electrons are generated in conduction band, yes, the material conduct current. Okay, so these two are very very essential point you should keep in mind. Okay, okay, right. Listen, students, why at 0 Kelvin the material acts as insulator? Anyone?
No thermal energy is there and no movement of electrons.
Yes, very good. And you know very well, in the valence band electrons are localized. In the valence band electrons are localized, they cannot conduct current. Okay, good. Yeah. Any doubt in this, student? Any doubt? Is it clear?
Yes, sir.
Yeah, good. So this is regarding intrinsic semiconductor. Intrinsic means pure semiconductor. Now what I'm going to do, I'm going to discuss the second type of semiconductor called extrinsic semiconductor. Let me write here. Extrinsic semiconductor, also called doped semiconductor. Okay, right. In extrinsic semiconductor, what we'll do is that we'll take some host crystal. I have told you, we'll take silicon, germanium, gallium arsenide, and we'll add some impurity. Okay, the addition of impurity, see, we'll take some host crystal, very specifically semiconductor material, right? Pure semiconductor material, host crystal, like silicon or germanium or gallium arsenide, etc. Many materials are there, etc. We will take some host crystal. To this host crystal, we will add some impurity. Therefore, what will happen? See, silicon, germanium, gallium arsenide, they are already semiconductors. They are all intrinsic semiconductors. But because of addition of this impurity, what will happen? You will get a new material having some impurity. That new material shows high conductivity. So addition of impurity increases the conductivity of the material. Right? So by adding impurity, if the conductivity increases, we call those semiconductors as extrinsic semiconductor. Extrinsic semiconductor. Okay, so students, keep this in mind. Silicon, germanium, gallium arsenide, these are all examples for intrinsic semiconductor. But in intrinsic semiconductor, conductivity, electrical conductivity is generally low. Why? Because the number of electron in conduction band as well as number of holes in valence band, they are all very less in number, because the electrons and holes are generated only because of thermal energy. So number of electrons, number of holes, they are equal. That's correct. But the numbers are very less. Therefore, intrinsic semiconductors, okay, generally show less conductivity. They show less conductivity. That's why in most of the electronic equipments, okay, people won't prefer intrinsic semiconductors. Okay, so let me write that point, so that this is also very important. Listen, electrical conductivity, this is under intrinsic semiconductor. Electrical conductivity of intrinsic semiconductor is generally low. Electrical conductivity is low. Therefore, it is of less importance, right, in electronic industry, right? Or so it is less preferred. It is less preferred to use as electronic is it proposed to use for daily purpose, okay, or for energy creation, etc. Okay, so it is less preferred. Let me just use the word less preferred. Why it is less preferred? Because electrical conductivity of intrinsic semiconductors are generally low. Why it is generally low, students? Why it is low? Conductivity of intrinsic semiconductor is low generally. Why? Very simple. See.
Addition of impurity.
Yeah. Yes. Yes, Aditi. Yes. We'll get electrons in conduction band. We'll get holes in valence band. Those things are correct. But the number of electrons and number of holes are less in number. They are very, very less. Therefore, electrical conductivity is low. Why? Because these electrons and holes are generated only because of thermal energy. Okay, that's why the number is very, very less. Right? So, electrical conductivity of intrinsic semiconductors are generally low. That's why it is less preferred in electronic industries. It is less preferred. Right? This is another important point you should keep in mind. Now I'll go back to extrinsic semiconductor. So in extrinsic semiconductor, I have told you, you take a host crystal. Host crystal are also semiconductors, but they are all intrinsic. Now I am going to add some impurity. Because of the addition of impurity, what will happen? Conductivity of the material increases. We call those materials as extrinsic semiconductors. Okay. Now I'll take elemental semiconductors like silicon and germanium. Okay. Say for example, I'll take silicon. Silicon and germanium, they belong to group 14 in the periodic table. Group 14. Students, observe carefully. I forgot to say this point. Listen, addition of impurity to the host crystal is what we call as doping. Right? Doping means addition of impurity to a host crystal to increase the conductivity of the material. It's called doping. That's the reason why extrinsic semiconductors are also called as doped semiconductors. Okay, right. Listen, the elements like silicon or germanium, they belong to group 14 in the periodic table. They belong to group 14. Now what I'm going to do, I'll take silicon which belongs to group 14 in the periodic table. To this, I'm going to add some impurity element from group 15. Say in group 15 we have plenty of elements. I'll take phosphorus or arsenic. Students, listen carefully. This is host. Group 14 element is host crystal. To this, I am going to add group 15 element. Okay, you can add either phosphorus or arsenic. If you add phosphorus or arsenic, okay, to the silicon, you will get huge increase in conductivity. Okay, and you'll get a material, we call that material as N-type semiconductor. Okay, I am adding group 15 element as impurity to group 14 element. So whenever you add group 15 element to 14, you will get N-type semiconductor. Similarly, if you add element from group 13, so in group 13 we have boron, indium, right, gallium. Okay, many elements are there, right? Many elements are there. If you add boron, indium, anyone to this silicon, okay, so I'm adding group 13 element to group 14. Whenever you add group 13 element as impurity to group 14 element, okay, group 13 and group 15, okay, are impurities. Group 14 is the host crystal. So I'm adding group 13 element as impurity in group 14. You will get what is called P-type semiconductor. There are two types, N-type semiconductor and P-type semiconductor. When you get N-type, students, when we will get N-type semiconductor?
An impurity is added from group 15 to group 14.
That's all. Yes. When impurity is added to group 15 to 14, you will get N type. If impurity is added from group 13 to 14, you will get P type semiconductor. Okay. Here N represent negative. N means negative. P means positive. That's all. Y negative, Y positive, we'll see. So N type semiconductor and P type semiconductor. There are two types. Okay. So in extrinsic semiconductor, we have two types. What are the two types? N type and P type. Okay. So let me write in the next page. So in extrinsic semiconductor, we have two types. Okay. We have two types. One is N type semiconductor. The other one is P type semiconductor. We have two types. Okay. N type semiconductors are obtained whenever you add group 15 element to group 14. If you add group 15 element to group 14, okay, I am adding group 15 as impurity. This is impurity. If you add group 15 element as impurity in group 14, okay, you will get N type. Whereas if you add group 13 element as impurity to group 14 element, will get what is called P type semiconductor. Simple. P type semiconductor. So in extrinsic semiconductor, there are two types. Okay, N type and P type. Now, what's the reason for the symbol N and what is the reason for the symbol P? I have told you N means negative, P means positive. Why it is negative, why it is positive? What's the reason? The reason is this. Students, observe this carefully. In the silicon crystal, pure silicon crystal, I have told you each silicon atom is connected by adjacent silicon, or it is connected with adjacent silicon through covalent bonds. Okay, there are a lot of covalent bonds are there. It is connected with adjacent silicon through covalent bonds. Let me just show like this. Okay, so pure silicon material where this covalent bond, right, extends in all possible directions, three-dimensionally. And I have also told you in pure silicon, this is pure. In pure silicon, at 0 Kelvin or at low temperature, the electrons present in the bonds, the electrons which are present in bonds, they are called localized electrons. I have told you they are called localized. The localized electrons, right, they do not conduct current. Now what I'm going to do, I'm going to add some impurity. Okay, say for example, I'll take a group 15 element, say phosphorus or arsenic. I'll take arsenic. The symbol is AS. Listen, group 15 element, students, here listen, this is very important. Number of valence electron for silicon is 4. So each silicon atom shares 4 electrons with the neighboring silicon atoms. Okay, but all the 4 electrons of silicon are localized because they are in the bond now. They are localized. But group 15 element, arsenic or phosphorus, if you take, they have 5 valence electrons. Okay, group 14 element has only 4 valence electron. So all the 4 electrons are involved in bond formation. So all the 4 electrons are localized now. All are localized. Now what I'm going to do, I'm going to add an impurity from group 15 which has 5 valence electron. So what it will do, it will replace some of the silicon atom in the crystal. Okay, suppose I'll replace this silicon by arsenic. Okay, so I have arsenic atom now, and now this arsenic atom, right, is connected with the silicon atom. See, silicon is the host crystal. 1 or 2 silicon atoms or only few silicon atoms are replaced. Only few silicon atoms are replaced by arsenic atom. That's the meaning. Here, just for understanding purpose, I have shown only one arsenic here. But keep this in mind. You will have some number of arsenic atoms. But number of arsenic atom is very less compared to number of silicon atom, because silicon is the host crystal here. Okay. But listen, arsenic has 5 valence electron. But out of 5 electron, 4 electrons are involved in bonding. 1, 2, 3, 4. Only 4 electrons are involved in bonding. What about the 5th electron? The 5th electron remains free. 5th electron of arsenic remains free, and this electron can move freely throughout the crystal. We call this electron as delocalized electron. It is called delocalized electron. Bondla irundha localized. Bondla illama free ah irundha adukku peru delocalized. Okay? The delocalized electron, they can move freely throughout the crystal. Okay? These delocalized electrons are responsible for the electrical conductivity of this material. Right? Now, students, observe this carefully. Now, which species is moving freely? Which species? Which species is moving freely here?
Negatively charged species.
Negatively charged electron, right? Okay, electron which carry negative charge. That's why it is called N-type semiconductor. N-type semiconductor, because here the carriers are electrons. Okay? Yes, take down. So when you add arsenic atom replaces some of the silicon atoms in the material, so that you will get N-type semiconductor. In N-type semiconductor, we have free electrons. So the free electrons, are delocalized. I'm sorry, we should not call it as a free electron. It should be a delocalized electron. So in semiconductor, we have, especially in N-type semiconductor, we have delocalized electrons. These delocalized electrons are responsible for the electrical conductivity. Is this clear, students? Any doubt? Good?
No, sir.
Yeah. Yes. Now go to the next one. So electrical conductivity in N-type semiconductor, right, is due to mobility of right, is predominantly due to, I'll use the word like this, is predominantly due to mobility of this delocalized electrons. Delocalized electron is behave like free electron, that's all. You can say all free electron, nothing wrong in it, but we are using this word delocalized. So electrical conductivity in N-type semiconductor is predominantly due to the mobility of delocalized electrons. Okay? Yes. Why I am saying predominantly? What's the reason? The reason is, listen, students, in N-type semiconductor, I'll take, say for example, I'll take silicon, where you'll be having valence band and conduction band. Observe this carefully. So this is valence band, this is conduction band, and you all know that valence band is fully filled, conduction band is empty. Okay, I'll take, for example, I'll take silicon. In this I will add impurity as arsenic. Okay, the element which is shown in within bracket is the impurity element, and this is host crystal. Okay, so in the host crystal I have added arsenic impurity. Listen, since the host crystal is silicon, the band gap is 1.1 electron volt. 1.1 electron volt. That's clear. Now, when you add arsenic, Students, observe carefully. Arsenic atoms, see, arsenic atoms donate extra electrons, right? Due to the addition of arsenic, you'll get extra electrons. So we call arsenic atom as donors. Okay? In n-type semiconductor, this group 15 elements, right, are the impurities. Impurities are also called as donors. Why they are called as donors? Because they donate extra electrons. Okay, so these donors, they create a level near the conduction band. They will create a new level near the conduction band. So this is called donor level. I'll write here. This is called donor level. This donor level has plenty of electron. Here we have plenty of electrons. Donor level has plenty of electron. Now listen, the gap between, students observe this carefully, the gap between donor level and conduction band is very, very close. Therefore, these electrons from donor level can go to the conduction band. Therefore, you will get more electron in conduction band. And due to thermal energy also, electrons will go from valence band to conduction band. Students, observe carefully. Electrons not only moving from donor level, electrons are also moving from valence band to conduction band. This is due to thermal excitation. Okay, so when electrons move from valence band to conduction band, it will create holes. It will create holes. Now the question is this: if you compare number of electron in conduction band and number of holes in valence band, are the two equal? Why? Why they are not equal? See, if electrons and holes are generated only through thermal excitation, then only number of electron in conduction band, number of holes in valence band should be equal. But now some electrons are generated, or some electrons starts to appear in conduction band due to donor level. Therefore, the number of electron in conduction band is very high compared to number of holes in valence band. Okay, so in n-type semiconductor, this is very important. Note down, in n-type semiconductor, number of electrons in conduction band is very much greater compared to number of holes in valence band. Okay, number of electrons, because the electrons not only comes from thermal excitation, the electrons are also arises due to donor level. Okay, so number of electrons in conduction band is very huge in number compared to number of holes in valence band. Okay, that is why, since electrons are very huge in number, we call this as majority carriers. Majority carriers. So in n-type semiconductor, majority carriers are electrons and minority carriers are holes. Carrier means charged species, okay, which can move. Okay, moving charged species are called carriers, right? In n-type semiconductor, majority carriers are electrons, minority carriers are holes. That's why this semiconductor is called n-type, because majority are electrons. Students, is this clear? Any doubt here? Any doubt?
No,
If you
sir.
find any difficulty, you please tell me. Any doubt, student? Any doubt?
No, sir.
So now you have huge number of electrons in conduction band and you have few holes in valence band. So conductivity of the material increases in larger extent. So n-type semiconductors conduct larger amount of current compared to intrinsic. Okay, yeah, this is very important. Keep this in mind. This is called N-type semiconductor. So in N-type semiconductor, you will get donor level near to conduction band. Okay, and number of electron in conduction band is greater compared to number of holes in valence band. Students, remember, electrons in conduction band will give conductivity. Holes in valence band also give conductivity. So in N-type semiconductor, plane, but it extends in third dimension. This is pure silicon. In pure silicon, I have told you all the electrons are localized. They cannot move. Okay. But now what I'm going to do, I'm going to replace silicon by some group 13 element. Okay, in group 13 we have boron, aluminum, gallium, indium, right? I'll take indium. Right, I'll take indium, the element indium. Indium has only 3 valence electrons. Students, listen carefully. Indium has only 3 valence electrons. So if I replace silicon by indium, what will happen? Okay, now in the place of silicon, I'll put indium. Okay, only few silicon atoms are replaced, and remaining crystal exists as such. Crystal structure should remain as such. It is called matching impurity. Okay, you should not add large size atoms or very small size atom. You should add impurity atom. The impurity atom size and the host atom size should be comparable. Okay, size matching should be there, size matching. Otherwise, the crystal structure will become different. Okay. Now listen, students. Since indium has only 3 valence electron, okay, so using the 3 valence electron, it can form 3 bonds. It cannot form 4th bond. So in the 4th bond, okay, this silicon will give 1 electron, but here there is no electron. It become a hole. That become a hole. Hole means positive charge. You will get a hole. Okay, and I have told you, whenever holes are created, yes, these holes also starts to move, okay, throughout the crystal. Therefore the material shows conductivity. So here conductivity is due to holes, predominantly due to holes. Okay, so whenever you add group 13 element, right, in group 14, right, what will happen? Holes are generated. Okay, see here what it will do actually, how it will conduct. See, from adjacent bond, students listen carefully, from adjacent bond, the bond breaks so that you'll get electrons. These electrons will jump to the hole. It will occupy the hole. Therefore, when this electron jumps here, this hole will disappear. You will get a new hole here. You will get a new hole here. Then another electron from adjacent position will jump here, and you will get a hole there. So actually it is electron moving, but in the material it appears like holes moving. Is this clear, student? So indium, due to a vacancy, indium will accept electron from adjacent silicon atom. Therefore these impurities are called acceptors. Students, in p-type semiconductor, the impurity elements are called acceptors. In n-type, impurity elements are called donors. In p-type, impurity elements are acceptors. Why it is called acceptor? Because you will get a hole here. That hole will gain 1 electron from the adjacent silicon bonds. the silicon bond breaks, so that electrons jump, okay, from this atom to the indium. So this hole will disappear. You will get a new hole here, new hole. Similarly, another electron will jump from here to here. You will get the new hole here. So the hole starts to move throughout the crystal. Since indium accepts electron, it is called acceptor. Okay, so if you in the band structure, let me show you in the band structure. In the band structure now, if you arrange energy, this is the valence band and this is the conduction band, valence band, conduction band. As I told you before, valence band is fully filled. Okay, so I have take for example, I'll take silicon crystal and I dope silicon with indium impurity. Okay, indium will generate what is called acceptor level near valence band. This is acceptor level. Acceptor level is generated near valence band. What this acceptor will do, acceptor will gain electron from the valence band. You'll get electrons. Electrons will go here. Whenever electrons goes here, you'll get many holes. Students, listen carefully. Acceptor level is close to valence band. So acceptor level gains electron from valence band. Therefore, you'll get more holes in valence band. Not only that, due to thermal excitation also, you'll get holes. Holes are generated, okay, are also due to thermal excitation. Now, see, compare the number of holes and number of electron, which is more in number?
Number of holes.
Students, compare number of so it is very clear. In valence band we have more holes. Okay, so in p-type semiconductors, right, number of holes in valence band is very much greater compared to number of electrons in conduction band. Okay, so in p-type semiconductor, holes are majority carriers. And the electrons are minority carriers because they are few in number. Since majority are holes, I have told you holes means positive charge. Since majority are holes, this semiconductor is represented as P, positive, p-type semiconductor. Okay, based on majority carrier, we are saying that it is n-type, it is p-type. Okay, is this clear, student? Any doubt?
No, sir.
Any doubt? Yeah, keep this in mind. Very important. Okay, with this we have completed the semiconductors. Insulators I am not going to teach because in insulator the band gap is greater than 3 electron volt. Therefore, electrons and holes are very few in number. So conductivity is extremely low. Therefore, we are not going to bother about insulators here. Okay, so remember, in metals band gap is 0. In semiconductor band gap is less than 3 electron volt. In insulator band gap is greater than 3 electron volt. Okay, right? Keep all these things in mind. They are very important. I stop here. In the next class, I'll give you the applications of semiconductors. What are the applications of n-type, p-type semiconductors, right? And when you join an n-type with a p-type, we can also connect like this. You take an n-type semiconductor and p-type semiconductor and join them. Listen, just for understanding purpose, I am saying simply join them. It is not doing. We are not doing like that. Okay, there is a process available. Okay, you can connect them, right? So when n-type and p-types are connected, what will happen? You will get diodes. PN junction diodes are produced, and these diodes have lot of applications, right, in electronic industry. Diodes are actually used as rectifiers. Okay, and we also have transistors. Transistors are used as amplifiers. Okay, yeah, we'll discuss those things in the next class. Once we complete this, then we have one more part called the magnetic properties. We'll discuss magnetic properties in the next class, and I'll try to complete this chapter by next class. Okay, yeah, I stop here. If you have any doubt, you can ask me now.